everybody. Oh, sorry, I just didn't realize my Zoom was on a different screen that I was looking at. Like, where is everybody? Let's do the usual things. My video, chat. Give you guys the attendance. There's the attendance as usual. Let's see, I want to say a couple things. I posted in Canvas a final review of sorts. I think it's pretty decent. There might be a couple questions in there that might not be super applicable, but I feel like most of them are pretty all right. So I would encourage you all to work on that if you were looking for more problems to do. I also did post the solutions in there, which won't become available. I think they become available either today or tomorrow. So I would definitely, if you're looking for more problems, look at the final review in Canvas. It's under modules. It's right at the top of the module. So if you just go to modules, you should see it right there. Also, I want to let you all know that apparently all of the colleges except for the College of Letters and Science have announced today that the pass no pass grading option that's allowed for spring for courses offered by their college. Basically, there won't be any issues with classes. Gosh, sorry, the statement here is not worded very well. Let me find this thing real quick. 1 second here. One second. Imagine most of you are probably in the College of Bio and Sci, but so the policy is such that students who are both in good and not good standing can change the grading option to pass no pass for both major and non-major courses. If you're not in good standing, I think you have to contact someone today. But if that's something you're thinking about, it shouldn't affect whether or not you're taking it. Like, it shouldn't matter whether or not it's a class for your major or a class that's not for your major. So if you want to take this class, pass no pass, and this class is for your major, not this class, I mean the 17A class, if you want to take that pass no pass, it shouldn't be a problem if it's a major requirement. Yeah. And it says here, for at least for the College of Biosci, students must request a change in their grading option to pass no pass grading via schedule builder by 11 p.m. on the last day of instruction, which is tomorrow. Yeah. So if you have any questions about that, let me know, or contact someone in your department or major or the college. All right. I think that's all I wanted to say about that. But again, if you have any questions, feel free to ask. I also posted in the discussions a place for you guys to request videos for me to make. I will try my best to make as many things that are asked for. So that is there for you as well. Also, sorry, a few things. Also, under announcements, I did post my office hours schedule for the rest of this week and finals week. So in fact, let me click on that for you guys. So let me share my screen just 1 sec. So if you look at this, if you click on the announcement, office hours for finals week, you'll see there's a Zoom link to each of the office hour times. Today from 3 to 4, tomorrow from 1:30 to 3:30, Friday from 2:30 to 3:30, Monday 1 to 3, Tuesday 10 to 12, Tuesday 1 to 3, Wednesday 10 to 12, Wednesday 1 to 3. And then if anyone needs anything on Thursday, I can also be available. But I felt like most people's finals finished up by Thursday, so I didn't schedule anything for Thursday. But if you need help on Thursday, I will still be available. Let me stop sharing my screen. So I think that's all the stuff I wanted to say. As usual, let me know. Yeah, so I will be posting the answers, Alejandra. I don't remember if I scheduled it for today or tomorrow. I wanted to give you guys a little bit of time to work on it without the temptation of looking at the solutions. But let me look at what I scheduled. I have it scheduled to be available tomorrow at 5 p.m. If you need it to be earlier, I can make it earlier. But if I would generally, I would like to give you time to work on it without having the solutions right there. But if you want them made available sooner, I can definitely do that. So just let me know and I will make them available sooner if that's something that you want. Also, no, that's not, sorry. So I would also encourage everyone to stay, what I'm looking for, to pay attention to anything your professor says in the next couple of days. I know a Math 17C professor just made his final optional for all the students. So that is something that is still potentially possible for any professor. I know these are wild times we're living in, so just be aware that your final situation might change or might be made optional. I wouldn't count on it if it hasn't happened already, but it is something that might happen. Okay, I think that's all the business stuff I wanted to say. I know people have been asking for specific examples. Specifically, the things most people have asked about are more optimization, more L'Hopital, and something else. I guess related rates. It's probably another thing. So I can do some examples of those things. Actually, let me. I can do this over here. Sorry, everything's in the way. Again, if there's specific things you would like to see that I am not saying, let me know. I'm also happy to do problems from the review I posted if you want to see any of them done in more detail. Although I do think the solutions now, that looks gross. Where did I put that? Sorry, 1 second. Try and make this look not so terrible. Problem with the orange pen is it just, I don't know, it feels like the orange dust is so visible. And to be honest, I'm really kind of focused. So, 1 second, please. I accidentally closed the book and had it open to the page. Stuff I wanted. Sure. Okay. So let's look at some, let's start with some L'Hopital rules example. Okay, and also I forgot to pull up the homework. I always have the homework up. Let me take a look at the questions you were asking about. Let's take a look here. Sorry, 1 minute. Sanders, files, homework. 9. Let's see, you're asking about questions. Oh, it's a new homework. Sorry, I haven't looked at this one yet. Okay, cool. Yeah, we can definitely do one like number 1 and 5. Oh, that's a new flavor of question that we haven't seen. I'm guessing he talked about this in class. Huh. Okay. Sure. Stability. Okay. So let me ask you guys, in what context did he talk about stability? Did he talk about showing the derivative was negative? Or did he do something else? Did he talk about cobwebbing? Anyway, I'll start doing one like number 1, but if anyone has an answer to that question about how he talked about determining stability, that would be good for me to know. I won't lie, I wasn't expecting to see that on this last homework. Not that it's not valid and useful. It is definitely something you'll continue to do in future classes, but I was just a little surprised.
He did mention cobwebbing and stability criterion.
Okay.
That was it, yeah.
Okay. We can definitely, yeah, I think I'll have to remind myself, I can exactly look in the book. I'm pretty sure I know what this is. So, yeah, let's look at something like problem 1, though. So, okay, all right. So these questions, I do like his questions in that they're trying to get at you actually writing stuff in a useful way. So let's say, sure, why not? I'm going to do, so a box with a square base and an open top, meaning it only has 5 sides, has a surface area of, I don't really know it. Let's say, sure. Let's say, let's say 60 square meters. It's probably not going to turn out to be a very nice number. That's fine. Stuff happens. Let V denote the volume of the box. And X denote the length of one side of the base. Okay. So he's really kind of spelling it out here. Find the formula for the volume in terms of X. So usually nobody says, like, so usually if I was writing this question, I would just say a box is a square base and an open top and the surface area is 60 square meters. Maximize the volume, right? But he's giving you kind of step by step. So we're going to draw the picture of our box that has a square base. Right, so there's our box, and this side is X, and this side is X. And usually we label the other side Y, or H. I'm going to pick Y. And we know the equation for the volume of a box is just the length times the depth times the height. So the volume is given by X times Y. And we know that we actually don't know what the volume is. So there's the volume as a function of X and Y. Now the question he's asking says, find the formula for volume in terms of just X. So what we need to do is we need to use the fact that the surface area is 60 square meters to find a constraint. So the equation for the surface area of my box that doesn't have a top is the bottom area, which is X squared, plus all of the side areas. And each of these 4 rectangles has an area of X times Y. So all 4 of them together is 4 times X times Y. And we know that that's equal to 60. In his problem, since the box has 6 sides and it's not an open top, your surface area equation would be 2x squared plus 4xy equals whatever value he has for the surface area. I think it's 54. And then since we want to write the volume as a function of just x, we're going to take this equation, we're going to solve for y, and then we're going to replace the y here with what y is equal to over here. So I'm going to subtract x squared. So 4xy equals 60 minus x squared. And then I divide by 4x. So that y equals 60 minus x squared divided by 4x. And then that is going to replace the y here. So that now I can write the volume as x squared times 60 minus x squared over 4x. And now I would probably simplify it, although it doesn't say to. but now we've written the volume as a function of just x. Or we found the formula for volume in terms of x. So I'm going to write this on the other side because I do want to do the second part of this problem as well. So volume as a function of x is x squared times 60 minus x squared over 4x. And since I know I'm going to try and find where the volume is maximal, I know I'm going to end up taking the derivative of this, right? So part 2 of this problem is what is the maximum possible volume of the box in problem 1? So to find the maximum possible volume, we have to take the derivative, so equal to 0 to find the critical values. Before we can do that, or not before we do that, what we should do before we do that is simplify this so that it's easier to differentiate. Specifically, I can cancel an x here and an x here. And then I can distribute this remaining x to the other two terms. So I get that the volume is 60x minus x cubed over 4. And if I divide each thing by 4, I can write this as 60 divided by 4 is 15x, and I've got 1/4 x cubed. Again, my numbers are not going to be very nice. That's okay. He says specifically, find what's the maximum possible volume of the box where x is between 0 and 3√3. So I kind of want to talk about how he's getting that because he's definitely asked you questions about that before. So how would I be getting my constraint here? Well, how is he getting his constraint actually? Oh, sure. So here's what so let me talk about that because here's what he's saying. So I went over on the side here in a different color just to kind of point out what he's saying. So he's saying he's got some box and maybe it looks like this, right? Maybe it's flat. And he's got x and x and y. And we know that the surface area is 54. And what he's saying is that x has to be less than 3√3. Say less or less than or equal to? Less than or equal to. Okay. And so the reason he's able to say that is because if you think about this, the bottom area is x squared and the top area is x squared. X squared, which is 3√3 squared, is 9 times 3, which is 27. And if you have the top and the bottom both having an area of 27, then the surface area is 54. So what he's saying with this in that problem is that x has to be less than or equal to 3√3 because if it was any bigger, it would eat up all the surface area that we've been given to work with. In the same sort of way here, I could say that since my surface area is 60 square meters, I can say that since I only have the bottom and not the top, I could say that x has to be less than or equal to the square root of 60. Because if x was the square root of 60, I'd essentially just have a flat box, which would be dumb. And then x has to be bigger than 0. This part isn't, well, it's a little important actually. I was gonna say it's not super important, it's kind of important. Because it's gonna help us figure out what we've got going on here. So now I'm gonna find my critical values. They're probably not gonna be very nice. So my derivative is gonna be 15 minus 3/4 x squared. I'm gonna set that equal to 0. I'm gonna add this to the other side. I'm gonna multiply by 4, which is gonna be 60, I'll divide by 3. So, and that's gonna be 20 equals x squared. So I'm getting a critical value of x equal to the square root of 20, which is not as ugly as it could be. So here's what we've got. We've got x equal to the square root of 20 is a critical value. And we also know that x needs to be between 0 and the square root of 60. Okay. Again, I'm not exactly sure if Sanders really cares about this part of it, but a lot of teachers care about you actually showing the number you found gives you a maximum, right? All I know right now is it's a critical value. Maybe it's actually giving me a minimum volume. So we technically have to check. Now, if Sanders doesn't care if you do this, then don't do it. But if he does, you should. So here's my square root of 20 right there. And I'm looking at what the derivative is doing. So I look back at my derivative here. If I pick a number that is smaller than root 20, like 1, I don't want to pick 0 because 0 is at the end of my interval. So pick the next easiest thing to plug in, which is 1. I plug in 1, 15 minus 3/4 is definitely positive. So my derivative is positive, which means my function is increasing. I pick something bigger than the square root of 20, but less than the square root of 60. So I'm going to go as close to the square root of 60 as I can. It's still an integer. So I'm going to pick 7 because the square root of 49 is less than the square root of 60, and that's 7. But the square root of 64 would be too big. So plugging 7, 15 minus 3/4 times 7, that's math. I mean, I should be able to do this. 15 minus 3/4 times 7 squared. It should be negative. Let's double check. 49 over 4 is like 12-ish. Right? 48 over 4 is 12. And then 3 times 12 is 36. And 15 minus 36 is negative. Yeah. Now, really, most of the time, if they say you're trying to maximize something, it should be a maximum. So you can just draw this and pretend like you check values and actually don't check the values. So this means that on our interval, the function is always increasing before this point. It's always decreasing after. So we definitely have an absolute maximum volume at x equal to the square root of 20 meters. Now, did we answer the question? Not exactly. We found where we have a maximum volume, but the question actually asks us, what is the maximum volume? And there's two ways you can go about finding this once you know the critical value of x. One way would be just to plug this back in to the volume equation and say, oh, the volume of root 20 is going to be not pretty, 60 times root 20 minus root 20 cubed all over 4. That's not very nice, but it is an answer. The other way you could find it is you could actually go back and you could find the y value and then multiply x times y to get that. Oh, I feel like maybe I made a small mistake. No, I didn't. Okay. I would probably just do it this way though. So that's how you would do an optimization problem like number 1. Again, all he's taking the long route here, but all he's really asking you to do is, he's giving you a shape. He's saying you have a constraint. In this case, the constraint is that the surface area is 54 square meters. And then he's asking you to maximize the volume. He's just kind of breaking it up into a few smaller questions. Okay, so let me look in your textbooks to grab some examples that are similar to what he's asking you there. And I could probably just make one up. I don't know. I worry if I make one up, it's not going to come out very nice. And here it might actually matter a little bit more. So let me just look through real quickly. I've also got some L'Hopital's problems I can get to. Where do you guys look good? So let's see here. 1 second. Well, looks like it's section 4.5. Yeah. Cool. I'll flip right to it. Yeah. Sure. There's a couple ways we can do this. Okay, so let me grab the problem here. I'm gonna not get to 5. I'm gonna not do one like 5. Just say let's do ones more similar to 3 and 4 first, and then we can talk about one more like 5 because 5 is a little bit more effort. So let's say we have. He's grabbing ones right from the book too. I mean, I don't blame him. I would grab problems right from the book as well. So let's say we had something like x sub t plus 1 equal to 1 minus x sub t squared. And we want to find the equilibria of the difference equation and then classify them as stable or unstable. So how do we even find the equilibria? It's a good question. So the thing you want to think about is the equilibria is supposed to be a value of x sub t that if you plug it in, the next value is the same. So what could I plug in for x sub t here and get back the same value out? It's not immediately obvious. I think it's the square root of 1/2. But we can do the, in fact, maybe the numbers aren't particularly nice. So what we do, I usually replace both of these with the same letter, like L for limit usually. So I write it like that. And then I'm going to solve for L. So I'm going to add L squared plus L minus 1 equals 0. Yeah, this one's not particularly nice. I'm going to have to use the quadratic formula. So L is going to equal, let's see, -1 plus or minus the square root of b squared minus, how do we get square root of 1? Oh, I'm done. It's not the square root of 1/2. 1 plus negative plus or minus the square root of 1 minus 4 times 1 times -1 all over 2, which is going to be -1 plus or minus the square root of 5 over 2. This is not my favorite example. I mean, they are both, so both of these are equilibria. If you plug one of them in, you get the same thing back. So if you plug this number in, I could have picked a better example though. If you plug this number in, you'll get the same number out, or either of these, I should say, -1 plus square root of 5 over 2, or -1 minus square root of 5 over 2. But okay, that's fine. And then how do we classify them as stable or unstable? There's a couple of different ways. Yeah, that's probably the best way. I really want to show you my favorite way, but it's not actually in this section. Yeah. Yeah, I know. Well, I'm thinking of something slightly different. That's later. Okay, I was getting a little carried away for a second. So when I want to classify these, here's how we do it. So we think of this as f of x sub t. And yeah, that's fine. So then if we evaluate the derivative, so if we look at f prime of x sub t, it's equal to 1 minus 2 times x sub t. And for each of the critical values, or each of the equilibria, if the derivative is negative, oh, sorry, that's not right. If the derivative is less than 1 in absolute value, then it's, sorry, this is never the way I'm used to it. If the derivative is less than 1, it's stable. If the derivative is bigger than 1, it's unstable. And I should say absolute value. Looking at the absolute value of this. And this one is going to be a little bit tricky. So when they plug in f prime of -1 plus or minus the square root of 5 over 2 in absolute value, you get the absolute value of 1 minus 2 times that number. By the way, this is a special number. It's not really important right now. But this is the golden ratio. It's kind of cool. So cancel the 2's. And then I've got absolute value of 1 minus -1 plus or minus the square root of 5. So distributing the minus sign, I get the absolute value of 1 minus 1 is 2 plus or minus root 5. So 2 plus root 5 is definitely very positive. Right, so you're going to get two answers. You get the absolute value of 2 plus root 5, which is definitely bigger than 1. 2 plus root 5 is, I don't know, it's like 4 point something. 2 minus root 5 is definitely between 0 and 1, or the absolute value is between 0 and 1. Right? Root 5 is a little bigger than 2, so 2 minus root 5 is a little smaller than 0, and the absolute value is a little bigger than 0, but not bigger than 1. So what we can say here is 2 plus, or I should say, sorry. And so this is where it's a little bit confusing because I was trying to be a little too slick. So the plus 1 ends up actually being the minus 1, right? Because 1 minus the plus is going to be the minus. So that's actually that one. So -1 plus root 5 over 2 is the stable equilibrium. And the reason for that is because when we take the derivative and evaluate it at that value, we end up getting something that is less than 1 in absolute value. Let's do another example that has better numbers. So let me show you guys something a little bit better. Yeah. Sorry, this one was not the best it could have been. Let's look at something like x sub t plus 1 equals, sure, x sub t squared minus 3 divided by 2. Seems good. Yeah. So let's first find the equilibria. And I will say equilibria is a big part of 17B and 17C. So even though it might not be a huge part of your final exam or your final quiz, it is something you should devote some time to understanding for your future classes, because it's definitely going to come back a lot. So for finding equilibria, I'm just thinking about these as x or L. You can use any letter you want. You can use x this time. So x equals x squared minus 3 over 2. So then I would multiply both sides by 2, and then subtract 2x. So 0 equals x squared minus 2x minus 3. And then factor this, x minus 3 times x plus 1. So here our equilibrium, or equilibria, are x equal to 3 and x equal to negative 1. And here it's a little bit easier to see that they actually are equilibria. If we plug 3 in, we get 3 squared, which is 9, minus 3, which is 6, divided by 2, which is 3. So you plug in an equilibrium, you get it back. Same thing for negative 1. I plug in negative 1. Negative 1 squared is 1, minus 3 is negative 2, divided by 2 is negative 1. So that's the whole thing about being an equilibrium value, is when you plug it into your recursive equation, you get the same exact value back. Now, what about stability? There's something my brain is not quite. There's something I'm trying to think of that I know is not what's happening here, but I want it to be what's happening here. So there's a couple ways we can try and find stability. My personal preferred way, I think, is just using the stability criteria. I don't love cobwebbing because it doesn't feel super precise, because you're kind of just drawing pictures. I mean, I can do if you guys want me to do the cobwebbing for this, I'm happy to, but if not, I won't. So if you want to see the cobwebbing, let me know. Otherwise, I'm just going to do it the other way. So I'm going to let f of x equal x squared to minus 3 over 2. I'm just going to call f of x instead of f of x sub t. It's the same idea. And then my derivative here is 2x over 2, which is just x. Right? I could rewrite this if you guys really want this as 1/2 times x squared minus 3. And the derivative is 1/2 of 2x, which is just x. This one's actually super easy. Oh, this one's actually easy, but not in a way. So for x equal to 3, the absolute value of f prime of 3 is just the absolute value of 3, which is definitely bigger than 1. For x equal to negative 1, oh, so what does that mean? Is 3 stable or unstable?
Unstable.
Correct, definitely. On the other hand, if I plug in negative 1, I'm just going to get, well, again, the derivative is just x. I'm going to get the absolute value of negative 1, which is 1. Well, what does that mean? Is it stable or unstable? And the answer is neither. We don't actually know. Right? If you look at the stability criterion, it only talks about if it's less than 1, if it's bigger than 1. It doesn't say anything about if it's actually equal to 1. And I believe if it's equal to 1, we don't actually know. Yeah. I don't think cobwebbing would tell us either, because I think cobwebbing, you get some sort of like, no, I didn't mean to close that page. I think if it was in cobwebbing, you would get something where it kind of just went around and around and around, but didn't either get closer or further away. I guess I'll do the cobwebbing, sure, why not? So I'm going to try and do the cobwebbing here. It's been a while. I'm not great at it. So, yeah. So here's how we do the cobwebbing, right? We graph this thing. I'll try and do my very best to draw a nice graph because it's probably going to really matter here. So, on the x-axis goes x sub t, on the y-axis goes x sub t plus 1, so we're usually calling f of x sub t, which was x squared minus 0.2. Okay, so I'm going to graph this, and I'm just going to plot some points. And I know I have some equilibrium, right? If I plug in -1, I get back -1. Let me be very precise here. 1, 2, 3, 4. Okay. All right, so I plug in -1, I get -1. When I plug in 0, I get -3/2. When I plug in, let's go -2 as well. When I plug in -2, I get 4 minus 3, which is 1/2. So when I plug in -2, I get +1/2. So this is an upward opening parabola. When I plug in 1, I get 1 minus 3 is -2/2, which is -1. And back here. And then when I plug in 2, I get 1. When I plug in 3, I get 3. Okay, so here's what my parabola looks like. The vertex is right there at 0, -3/2. Okay, so let's see if we can do this cobwebbing thing. So the way cobwebbing works is you draw the line y equals x. We put that in as a color pen. And the line y equals x should go through your equilibria. Or x sub t plus 1 equals x sub t, right? This is y equals x, or x sub t plus 1 equals x sub t. And when x sub t plus 1 is equal to x sub t is where you have an equilibrium, right? So 3, 3, and -1, -1. All right, and then what you do, and I have to make sure I remember how to do this, is I see. So you start at a point, and you basically so you can start anywhere. You don't want to start at the equilibrium. So I'm going to start like here at x equal to 1, and I'm going to go up to, and I'm going to make sure I do this the right way. I'm going to go. You always go first. You go vertically to the actual function, and you go horizontally to the line y equals x. Okay, so let me start over here at 4, just because that seems more interesting. So I need to extend my graph a little bit. So if I were to plug in 4, I would get 16 minus 3, which is 13/2. 13/2 is like 6 points. So I would go up, way up here to this. And then I would go way over to this graph here. And then I would go up to the parabola that's way up there. So clearly, right, this is shooting me out that way. Like even if I start a little bit closer to 3, like if I start at like 3.1, we go up to the graph and then over to y equals x. And then again up to the graph, right? It keeps shooting me away from x equal to 3, which means that is probably unstable. I can also look at the other side of 3, so I start like at 2.5, and this is going to be a little more interesting. Let's say I start like right here, a little bit bigger than 2. Oops, so I always make this mistake. You're always going vertically to the graph, which is the black function, and horizontally to the line y equals x, which is the blue function. So I go vertically to the graph, and then I go horizontally over to the blue function. And then I go vertically to the graph, and then horizontally over to the blue function. And I go vertically to the graph, horizontally to the blue function. And then here's where I'm going to get trapped, because I'm going to keep going vertically to the graph and horizontally to the blue function, and then just end up in this little box where I'm not getting closer and closer into the equilibrium point. I'm also not getting further and further away. And that's kind of what's happening when you have the stability criteria end up equaling 1. It means you are not unstable, right? You're not going away from your equilibrium, but you're also not stable. You're not going in towards it. So that's what's happening with that particular value there. And the way you can also kind of think about it is if the derivative is larger than 1, it means the slope of this is super steep. And so when you do this up and over thing, this super steepness is going to push you way away from your value. Whereas if your slope is less than 1, you're going to be less steep, and so you're going to get pushed in towards your actual value. So let's do one more. Wow, time flies. Let's do an example like question 5, but not exactly question 5. So question 5. Sure. So I'm going to look at question 13 from the textbook, and then probably 14 as well. So I wouldn't think he would maybe make you do cobwebbing on your test or your quiz, but I could see him like giving you the graph of something that's been cobwebbed and maybe asking you to say something about that. Here is the attendance stuff again. So let's look at this one. So I've got x sub t plus 1 is equal to c times x sub t over 1 plus x sub t. And here, so in the problem he gives you guys, he says c can't equal 1, which I guess makes sense because if x sub t plus 1 equals x sub t plus 1, right? So this is the problem in the book, or in the homework. It's impossible for c to be 1 because then you're saying, well, you wouldn't have an equilibrium because this would always be exactly right. This plus 1 would never be able to be the same as that. So here c can't equal 1, which makes sense. Here, so again, we're trying to find the equilibrium of the difference equation. So let's find so we're just going to, again, just like before, we're going to replace every x sub t or x sub t plus 1 with x or L or whatever letter you want to use and solve for x. Most of the time, the first thing you want to do is get rid of any denominator. So let's multiply both sides by 1 plus x. So 1 plus x times x equals c times x. So I've got x plus x squared equals c times x. Subtracting this and rewriting this, I've got x squared plus x minus cx equals 0. Let's factor out an x. X plus 1 minus c equals 0. So I see two equilibria. I see x equal to 0 for sure. I also see this thing equal to 0, which means x equals -1 plus c, or c minus 1. So those are my two equilibria. And now we want to determine the stability of those equilibria. And it's going to depend on the values of c. So this one will just be whatever it is based on whatever we get. So let's find our, again, let's do, so the derivative. So f of x is c times x over 1 plus x. We have to use the quotient rule. The derivative is the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. I should factor out a c. So I end up with c times 1 plus x minus x is just 1. So I just end up with c over 1 plus x squared. Okay. Now, let's look at x equal to 0. So for x equal to 0, f prime of 0 in absolute value is just the absolute value of c over 1 plus 0 squared, which is just c. Really, it's the absolute value of c, right? Because c can be positive or negative. If I want this to be stable, that means the absolute value of c has to be less than 1. So for x equals 0 to be stable, we need the absolute value of c to be less than 1, which is equivalent to c being between -1 and 1. Something to be aware of here is if you have multiple, if you have multiple equilibria, they will have possibly different criteria for what the value of c needs to be so that you get stability. Let's look at the other one. I know I've kind of got, I'm going to have to erase some stuff here. So the other one is x equal to c minus 1. So I look at f prime of c minus 1 in absolute value. I'm just going to plug in c minus 1 for x. So I'm going to get c over 1 plus c minus 1 squared. This is going to be c divided by c squared, oh sorry, absolute values, which is 1 over c. So this is kind of interesting, actually. So if I want that to be less than 1, then I want 1 over c to be between 1 and negative 1, which actually means c has to be bigger than 1 or less than negative 1. Right? If c is bigger than 1, then 1 over c will be smaller than 1. If c is less than negative 1, like negative 3, then 1 over negative 3 will definitely be between negative 1 and 1, which is kind of the opposite of this, which is kind of neat. So here's what my final answer would look like. I would say that my equilibria are x equal to 0 is stable when c is between 1 and negative 1, or is in the interval from negative 1 to 1. And x equal to the other one, which I know I erased, I think it was 1 minus c. It was c minus 1, sorry, is stable when c is less than negative 1 or bigger than 1. So when c is an element of negative infinity to negative 1. So that's how you would answer a question like that. I do think the one, number 5, is a little bit easier. Well, let's go ahead and look at another one, because we still got 4 or 5 minutes. Sure, this one looks similar, but I'm sure it's different. So again, I'll remind you, for those of you that may have come a little bit late, there is a final review that I posted, and the solutions will post tomorrow at 5. Unless you need to see them sooner, I'm happy to get them to you sooner. Also, the College of Biosci made it so you're passed, if you choose to take class pass, no pass, it's perfectly fine if the major class or not. All right, let's look at one more. Let's look at this one. X sub t plus, every time I open a new black pen, I use it up way too fast. Let me try now using my new black pen way too fast. I conserve my pens here. Use a blue pen. Let's see, so let's do x sub t plus 1 equal to, what have we got here? X sub t over c plus x sub t. Okay, so first off, we're going to find the equilibrium. So we're just going to set x equal to x over c plus x. Multiply both sides by the denominator. You never want to divide by a variable, so you don't want to divide by x, or that would be a bad idea. So I'm going to just bring this over and multiply this, so I get x times c plus x squared minus x equals 0. Factor out an x, so c plus 1, plus x minus 1. So here we're getting, again, x equal to 0. And here we're getting, I think, actually the opposite. We're getting x plus, let's just write it out. If c plus x minus 1 equals 0, then x is going to equal 1 minus. You can check these if you want, right? If I plug in x equal to 0, that's not a c, that's a 0. 0 over c plus 0 is 0 over c, and I get 0 back. If I plug in x equals 1 minus c, 1 minus c over c plus 1 minus c. The c's cancel and I get 1 minus c over 1, which is 1 minus c. So I plugged in 1 minus c, I got back 1 minus c. So those are both equilibrium. Now we have to check to see what makes them stable. So first we'll take the derivative. So f of x is x over c plus x. f prime of x is the bottom, c plus x times the derivative of the top, which is 1, minus the top times the derivative of the bottom, which is 1, all over the bottom squared. And then simplifying the top, I get c plus x minus x over c plus x squared. So I just get c over c plus x. Okay. So there's my derivative. And now I'm just going to check the derivative at each of these values. The absolute value of the derivative. The absolute value of f prime of 0 is going to be c over c plus 0 squared. I feel like this problem is very similar to the previous problem. Sometimes that happens. Which is going to end up being 1 over c. If I want that to be less than 1, we already know what happens there. We know that c has to be bigger than 1 or c has to be less than 1. And then for the other one, I feel like it's going to be the opposite. We're looking at f prime of 1 minus c, an absolute value. I'm going to get, I'm just going to plug in 1 minus c for x. I'm going to get c over, I'm going to get c over 1 here. It's kind of weird that these problems are kind of the same but different. C over 1, just c, I want it to be less than 1. So here I get c between -1. So that's the, so for problem 5, you're going to do the same sort of thing. You're going to find the equilibrium by just setting, so problem 5, you're going to find the equilibrium by setting x equal to c times x plus 1. And you're going to solve for x. And then whatever values you get, you're then going to plug into the derivative of this. Now, see, the derivative of this is interesting, right? If I look at this is my f of x, f prime of x is going to end up being just c. So for problem 5, your stability criteria is wholly dependent on what the value, I mean, they all are dependent on, but specifically, no matter what your equilibrium is, your derivative is going to be c. So any equilibrium is going to be stable if c is less than 1 or bigger than -1, and unstable if we're outside of that interval. So that problem is a little bit weird, but not too terrible. All right, hopefully that helped you guys with that stuff. Again, there's a discussion. If you want some videos, if there's specific things you would like to see videos made of, like specific problems or just topics in general, you can let me know. See, the x values in the equation has to be equal to 0. To get the x values, no. To get the equilibrium values, you're just setting these equal to each other. So you're solving this. I'm not setting it equal to 0. I don't. So the reason here I'm setting it equal to 0 is I set, like in this other equation, I set x of t plus 1 times c plus x of t equal to x of t, or I just use x, and then I brought everything to one side to make it easier to solve. But I'm not starting out by setting 0. I'm just using 0 to my advantage. Yeah. All right. So we don't officially have class on Friday, but I'm still going to meet at the usual time on Friday. So I will be here on Friday at 10 o'clock, just like regular class time. And you guys can come and ask me questions, or I can talk more about various things. So I will see most of you on Friday, I imagine, unless you have a test at that time. I also have an office hour today from 3 to 4, and an office hour tomorrow from 1:30 to 3:30, which are on the announcement that is in Canvas. All right, you guys, let me know if you have any questions in general, and I will see you all later. Bye.